It's a good it's a good time. So the interesting thing about today's video was sort of this like I don't know if it's a teaching moment, but I was sort of taken aback when this professor told me that like basically the only research that's interesting that's happening right now is computational work. And of course, as I said in the video, I definitely don't think that's true, but there is a real limit to analytical work. And as an undergrad, I came in and, I was really under the impression, as a naive undergrad, that you could just sit down and if you tried hard enough and you were smart enough, you could just solve anything. And like everything came down to analytics and, that's just what physics was. And that's obviously not the case. So I was wondering, did you have a similar experience or were you less naive than I was as a first year or a second year?
I guess maybe I want to say a couple of things about that. So I suppose maybe it's worth thinking about what we mean when we say solve a problem. I think it's before I studied physics in my undergrad, I was very interested in physics, but I hadn't really given too much thought to what it sort of meant when we said something like this problem is solved. What does that really mean? And I think that in the analytical domain, what we find nowadays is that perturbative methods that make various approximations that are, we say, well controlled. So approximations where we can understand exactly how the approximation fails and quantitatively why it fails.
Yeah.
This sort of dominates the school of analytic physics nowadays. I wouldn't say it's the only thing that people are doing, but that's a lot of what people are doing in non-trivial problems. And I think that it's meaningful for us to say that, that is a solution on some level.
That's fair.
That set of techniques does get us answers that we can compare to experiment, that we can use to understand the physics that's happening, say, at a phase transition. So I think that absolutely there are analytical methods. There's a vibrant community of analytical methods that attain a kind of a solution to a lot of these problems. And we just have to sort of be clear about what it means to solve the problem. So, in the context of the video that you put up today, there are definitely a lot of problems where getting a sort of exact closed form solution is just not going to happen.
Yep.
And people really do accept that solving the problem in that sense, solving the problem in the sense of I have this function, it's exact to all orders, there's no approximation behind it, and it gives me the exact quantity that I'm interested in, maybe the expectation value of an observable in an experiment. Definitely those problems are kind of, for the most part, solved at this point. Like you mentioned, we need to rely on either numerical techniques or on this family of new sort of high-tech analytical techniques that involve making various kinds of approximations that are well controlled. But even within that family, the thing is as well, right, that physics problems are not monolithic. As anyone who studies physics, as you well know, and as many undergrads who watch your channel will be learning, there are many different flavors to physics problems, and there are many different things that we're trying to compute. And sometimes solving the problem looks like coming up with a new mechanism.
Yep.
So for example, in the case of, you mentioned in the video, the insulator superconductor transition, that's an extremely interesting topic at the moment. There is a mechanism that was proposed in the 1950s to explain what we now call conventional superconductors. And beginning in the later half of the 20th century, people began to understand that there are superconductors for which this physics simply can't be the correct explanation. And so the quest is on to propose new mechanisms that generate superconductivity. And indeed, there's actually some recent work I believe by Liang Fu, where he and his collaborators propose a novel mechanism for superconductivity in these non-conventional materials.
That's really interesting.
And they treat that mechanism using a number of approximations, using numerical techniques. So they sort of bring to bear a large number of different techniques. Oftentimes, especially if you're going to propose a solution to a big problem, you're going to bring numerical techniques to the table, you're going to bring analytical techniques to the table, you're going to use them to corroborate one another. It's common that if someone introduces a new numerical algorithm and you're reading a paper that introduces it, they'll benchmark that algorithm to tried and true methods like exact diagonalization or DMRG.
Yep.
So I think that, what we want to imagine is that there's now a sort of family of techniques, and what solving the problem really looks like is understanding the physics. And we now just have many roads to get there. Some of those roads are computational, some of those roads are analytic.
Yeah, so that's definitely fair, and I think it's also worthwhile to point out that there's also a vibrant mathematical physics community that contributes things like no-go theorems, for example.
Absolutely.
That sort of narrows the field of like where you should be looking for specific phenomena, and of course they do many other things like very very important bounds like the Lieb-Robinson bounds.